All right. Hello. Olá, boa noite. Sejam todos muito bem-vindos. Welcome to everyone here. Today is going to be a little bit of a mixed language seminar. We have English and Portuguese because we have some guests overseas, which I will present shortly. My name is Mats. I'm a PhD student at LIVIA, and I will be the mestre de cerimônia. Então, vou falar português. Vou tentar falar português agora. My first language is not Portuguese, but I will try my best. So, então, sejam todos muito bem-vindos. Estamos iniciando o quarto seminário de comportamento motor, visão, aprendizagem e ação. Novos direcionamentos para esporte e as atividades humanas, organizado pelo Laboratório de Informação, Visão e Ação, LIVIA, do Departamento de Educação Física da Faculdade de Ciências da Unesp de Bauru. Para realizar a abertura do evento, convidamos também a compor esta transmissão a profa doutora Paula Fávaro Polastri Zago e o professor Dr. Sérgio Tossi Rodrigues, coordenadores do Laboratório LIVIA. Neste momento, possuo a palavra a Sérgio Tossi Rodrigues para a aberta oficial do evento.
Boa noite a todos. Inicialmente, eu gostaria de agradecer a participação de todos os inscritos no quarto Seminário de Comportamento Motor, Visão, Aprendizagem e Ação. Novos direcionamentos para o esporte e as atividades humanas. Esta quinta edição conta com a participação de 215 inscritos, sendo profissionais da área da saúde, como educadores físicos, fisioterapeutas, terapeutas ocupacionais, médicos, fonoaudiólogos, graduandos e pós-graduandos da área de comportamento motor e afins. Neste ano, a continuidade do evento irá abranger um maior aprofundamento sobre os aspectos que envolvem o controle da postura e os objetivos das tarefas concomitantes. Temos a presença do professor doutor Ruud van der Wiel e da professora doutora Audrey van der Meer, ambos da Norwegian University of Science and Technology, NTNU. Eu gostaria de agradecer ao Departamento de Educação Física da Faculdade de Ciências da Unesp de Bauru e aos membros do Laboratório de Informação, Visão e Ação, o LIVIA, que não mediram esforços para que o evento acontecesse. Sem mais delongas, eu, juntamente com a professora doutora Paula Fávaro Polastri Zago, desejamos a todos um excelente evento. Muito obrigado.
Para ajudar a responder qualquer dúvida que aparecer, vamos iniciar agora nossa sessão de palestras. Ao final das palestras, os palestrantes irão responder as perguntas do público, tá? A primeira palestra será ministrada pela professora Dr. Ruud van der Wiel, em Psicologia Cognitiva pela Universidade Norueguesa e Ciência de Tecnologia, professor na NTNU. Possui formação acadêmica em Educação Física, Ciência do Movimento e Psicologia, obtida em instituições dos Países Baixos e da Escócia. Sua palestra ministrada é intitulada As abordagens neurocientíficas tradicional contra ecologia na ciência do esporte. Por gentileza, professor Ruud van der Wiel, fique à vontade para iniciar a palestra. Ok. One moment.
Thank you very much. I'm continuing in English, and thank you very much for that introduction from Sergio and Mats. I didn't quite get what he told about me. I hope there's all good things, but if not, you just let me know in the comments if you said something naughty about us. What I'm going to talk about now is what we have called ecological neuroscience, and to put that as separate from what we have called in the lab traditional neuroscience. Now, that's not a derogative term about the neuroscience. It's just the terms we use in our lab when we talk about traditional neuroscience and ecological neuroscience, is to distinguish and what we try to achieve with a slight change in the more traditional neurosciences that would also capture the ecological bit by it. And what we mean by that is that we are in our work inspired by ecological psychology, particularly by James Gibson's ecological theory of perception, of which the optical flow concept and the affordance concept are central. Now, this is a very, from our point of view, from physical education, it's always been a very interesting point of view to explain how we couple perceptions and actions. In a sense that Gibson always was very taken by the fact that if we can distinguish variables in between the environment and the actor, that we can distinguish variables. For example, when we catch a ball, Gibson was taken by the fact which variables in the optical array are used to catch that ball. And he was not particularly interested in what the brain's involvement was in those sort of actions, because he argued if we know the variables in the environment, we can deduct from that something in the nervous system must react to that. Now, that was like 30 years ago in the 1979 book, he argued like that. And since that time, a lot of things have happened in terms of new technologies to actually measure the brain. So we are trying to enrich the traditional ecological psychology by involving the neuroscience, the nervous system in it, such that it's a more encompassing theory about we can use, and that also says something about the nervous system. So we to put that apart from what we call then the traditional neuroscience is, for example, later on, Audrey Vandermeer will be talking about our handwriting research, which we also carry out in the lab. And then we look at, for example, in the writing task, what brain involvement there is. Now, it turns out that this particular research has been used all over the world, as you can see in this particular picture. So it's very popular. So we do carry out what we call the more traditional neuroscience, but from our theoretical perspective, we like to try if we also can involve the nervous system in ecological psychology. And that's what I'm talking about. And that is where we pick up the idea of resonance, which I will conclude this presentation with. But what do we mean by ecological neuroscience? Now, in recent years, a couple of years ago, there was, for example, people in Berlin have now achieved very good equipment and analysis techniques, and they even now put on EEG nets on people's heads, and they release them in the city of Berlin, either walking or cycling. And then when they return to the lab, it's like a push on the keyboard, and the whole actions by moving through Berlin are analyzed straight away. So they call themselves also ecological neuroscience, just because of the fact that they are not in a lab any longer, but fixed head mounts, etc. They let people loose in the free with the equipment, and they can, in that sense, are measured in real ecological environments. However, this is really nice that we are moved out of the lab, but we think to perform ecological neuroscience, there's something extra from ecological theory necessary. And that's where James Gibson, with his direct perception theory, comes in. And as I just explained, Gibson explained an ability to filter the optic array as the potential to filter information through what he called resonance. It is like radio waves and the radio, which can pick up frequencies that broadcast music, etc., distinguishing from other noise. So people are able to tune into their environments fairly automatically. Now, that's easier said than done, because we also have to actually measure that. If people can tune into their environments automatically with the nervous system. He assumed that, but we are taking a little step further and try and measure if this resonance process is actually what is going on. And what he defined with a newly defining of a perception theory in the 60s, 70s, he designed the concept of optical flow and affordances many people have heard about. And it's particularly the optical flow concept that will be central in this presentation. So the optical flow is like the light that is picked up by the perceiver or the sports person or what have you, that is coming from the sun and then shining through the clouds. And by shining through the clouds, it's already taken on structure. And by bouncing further up on the environment, it will take even more structure. And the idea is of optic flow is that we not create that structure from the light sources, but we pick up, we differentiate the light shadings from the environment. So, for example, in this optical flow pattern, quite a common appearance for many of you driving a car in a built-up area. Now, the blue arrows indicate while you're driving what the potential information is that is available to you when you're driving. Now, you can interpret that in two ways. Either you can say, I use my brain to create all those blue arrows from the information from the picture. That would be a traditional processing, heavy processing achievement. However, you can also say, my brain and my perceptual system is there to pick up the invariance in the blue arrows. So the difference is that in the one interpretation, I create the arrows by computation in the head. And in the other interpretation is I take those blue arrows, they are there, that is structured information. And all I have to do as a driver is tune into the right arrows that are available there in order for me to carry out the task. Now, for me, that is the main difference between the traditional neuroscience, where you create the blue arrows, or you accept the information is detailed and structured, that you have to learn where to look in that information. It's as easy as that. So we change from the traditional, where we everything done computational, to the differentiation of the blue arrows. That is the difference we are making when we go from traditional to ecological neuroscience. And it is our supervisor, David Lee, who sadly passed away a couple of months ago, who not only he adapted Gibson's idea of the optical flow, of the blue arrows. And he said, well, he was a mathematician, and he said, how can we pick up those blue arrows without having to process them? And what he came up with is the concept of tau, which is the Greek letter for T for timing. The time to contact variable is a very general variable. It is indicated by the top figure looking at trees, mountains, the ground. And it is the time to contact that we are also in sports situation need to be able to pick up without the necessity of being needing to process all that information. If I walk towards a wall, from a traditional point of view, I need to measure my distance and I need to measure my velocity. And then I need to divide the distance by the velocity and I get the time. That would be heavily computational by a computer. However, David Lee, he designed the concept of tau, and he said, well, if an object is approaching you like a ball, it goes through the lens, and the triangles you see on the screen, at the right-hand side, they become smaller, and at the left-hand side, they become bigger. And in the middle, with the little arrows, that's the lens. So it's like upside down, and by the expansion on the retina, David Lee showed mathematically that you can pick out time to contact free of charge. So you don't have to process it. It's only picking up that information from the optical expansion on the retina that gives you that information for free. Now that's nice for the ecological psychology because you don't have all that processing going on. And you don't need to have that high cognitive load to do simple tasks like walking towards something or catching a ball. So, and that is by many different type of experiments have been not so much proven, but it is more sort of made likely that, for example, a bird that is diving into the water to catch a fish, at some point the bird has to flip his wings behind it because otherwise it will damage it on the water surface. Now it shows that birds that are starting their dive from higher altitudes, they end up with higher speeds towards the water, so they close their wings earlier than the birds that start their dive at lower speeds, showing that the timing window variable is actually what those birds use. It's consistent with the tau hypothesis, so to speak. And very similar also when infants reach for an object, they use the same type of strategy. So when an object is going back and forth on the track, as you can see on the top video, the top picture, babies start moving their hand when there's a certain time away. So there is 3 different speeds going from left to right. And the children allow when the movement of the target is very fast, they start their hand movement earlier. And when it's slow, they start later. So also here, there is a time window instead of a distance or an angle or whatever strategy that is less cognitively or more cognitively demanding. So he made initiation of the movement, like flapping wings or babies initiating an object, as a tau margin research. Whatever you read tau margin in the literature, it is when the babies or animals initiate their action. However, that wasn't enough, because when a baby initiates the action of catching, it's not enough to just know when to start your hand. It's also important to know how you can control your hand visually on a continuous basis when you're going towards the target. And that is what David Lee called in Edinburgh the prospective control. So you control your movements on the basis of perceptual information that is informing you about what's going to happen next. So we're moving from a tau margin, initiating the action, to prospective control, controlling the actions. And I have to explain you this in order to go to the nervous system a little bit later. So this is a very, very simple example to show how it is a tau function. That's what you see here on the screen. The tau of x, which could be anything at all, is defined by x divided by how it is changing. That is how the tau function is defined. And if you see the top graph you see on your screen, it could, for example, be a video recorder moving my hand in x direction. So when I pick up a glass of water, the hand in x direction goes up. So you see the hand is starting at 0, and then it goes up and up and up and up, and then I stop the hand. So this will be the distance of my hand, the displacement of my hand. That will be x. Now, if we want to see how my hand is changing, I need to differentiate the little red dots, because when I video this particular movement of my hand, it takes about 20 frames a second. So if I move 1 second, I have 24 dots on the first graph. If I measure the distances between the dots, that's called differentiation. You know how fast my hand is going. So x is the displacement of the hand divided by my velocity of my hand, and that will end up in a, let's look at the deceleration phase of the curve. We end up in a straight line. Then you can say the tau of x is kept constant with the time to contact. And if that is on a straight line, that is those variables you keep constant. That is what you control. And if you look at the actual, how the line is set into the graph, you can look at the slope of the line to see how are the two variables on the y and x-axis being controlled, in what kind of way. And there's various ways of doing that. We have a summary graph here that if the line in the graph is standing like it's between, the first one is bigger than 1, it means my hand is accelerating towards an object. Or if the slope of the line is between 0.5 and 1, it means my hand is decelerating towards the object. So in a way, we look with a microscope at movements to see how they are controlled on the basis of perceptual information. That is the crucial bit. We have prospective control based on prospective information. That's not the same as feedback. That is, prospective control is ahead of time. Okay. Now, this is the kind of the tools I need to show you how we're going to look at ecological neuroscience. If you understand this simple bit about moving your hand and the x divided by how it's changing, you end up with the tau curve, and the curve has a certain slope of the line, and that provides us with information about how the movement is carried out. And these are many different experiments in the last 20 years that have shown that this prospective control is actually working. And you see here different behavior tasks and also different human and animals. They all seem to boil down to a graph from low left to the top right. So there seems to be some underlying general principle of controlling these various actions. Okay, so now we go to the bit of the ecological neuroscience, where Gibson explained an ability to filter the optic array as the potential to filter information through resonance. So the perceptual information and the nervous system are resonating. They're not, the nervous system is not providing new extra information. the nervous system is reflecting or resonating what is happening in the environment. Now, and that's why I explained to you the tau function, because that is a really good method of measuring what I always call apples and oranges. They usually, you cannot add them together, but if you use the tau function, you can measure the input to the perceptual system in a visual stimulus, for example, and you can measure with EEG the electrical flow in the brain, and you can put on the one axis and the other axis in a tau coupling and see how those variables relate to each other. And that's basically, in a nutshell, what this slide says. So let's move to an actual experiment where we show visual looming stimuli to infants and to adults, but they work best when we use them with the infants. So what we do here, and this is the kind of ecological validity of the looming stimulus. In many sport situations, people have trouble with some looming danger. So this is the ecological validity, so to speak. And what we do is that we have a baby with an EEG net on, and we show 3 different looming stimuli. And, the quickest one takes 2 seconds to arrive. The middle one is 3 seconds, and the slow one is 4 seconds. So we send them to the baby, and they grow on the screen. And then for the baby, it is as if they're hitting them in the face. So they actually think they're real stimuli coming towards. So they're really good stimulus to engage a little baby. So we're measuring, we know the movement of the stimulus, so we can make the tau of this growing stimulus by x divided by how it's changing. We have the tau of the looming stimulus, and we have the activity in the brain, which can also be the electricity, how it's changing, and we couple them together. And this is what the baby looks like, the same baby when it's 5 months and when it's 12 months. So now you see what's happening in the brain when it turns around, and the stimulus will appear soon in the middle. And then you see, look at the 5 months and the 12 months, the green bit in the visual cortex, which will appear in the 5 months. It's happening, and slightly later and slightly more up the dorsal stream for the older children. So that is what the electrical activity looks like. And this is what the brain looks like between children between 5 months old and 12 months old. They do exactly the same, and we subtract the 12 months old, the 5 months old from the 12 months old, and you see the triangle here. There are statistically significant differences when the babies are 12 months. There's more activity in the occipital cortex and the right sense, so-called O2 area. So there is something has happened during the 7 months, and notably, babies also start to crawl around. So they start to move around and see how things move in the environment, and that it is our hypothesis from the lab that because of they initiate their movements, that the pickup of moving stimuli is better picked up, so to speak. Now we got the idea of a tau coupling to do this because there was some existing research in monkeys, where monkeys were in the laboratory and they were shown various light stimuli, like vertical, horizontal. You can see the yellow stripes in the left top corner. And every time the orientation of the light beam is changing, you see a difference in the pulse rate. You see by the red the red spikes on the screen. So that gave us the idea that information for the brain is translated in a spike rate, and the spike rate informs the animal what type of light it is looking at. Combine that with the fact of the looming stimulus, the tau of that, you can couple the tau, how it's growing, and how on the left bottom graph, how the reaction is in the brain. And if you look at the left bottom graph, there is 3 areas in that that are really standing out, showing that they're reacting to the looming stimulus. Now, if you remember the previous graph, we take the VEP of X, of the graph number A. That's the electrical activity that is belonging to a 2-second loom. And then you see that the black curve is the VEP, the actual electrical current. And if you measure the distances between the black dots, you end up with the red curve. And then you need to divide X by how it's changing. And so you have the visual angle at number B. And if you divide them also up between them, you plot the tau of the X against time, and you end up with a tau graph. And he's also, if you remember, the other experiments with many graphs that were from bottom left to top right, they also seem to be a regression line which is higher than 0.95. And because we look at the slope of the regression line, we can say something about how the brain is dealing with these speeds. And this is basically what we find. If you only look at the left-hand graph, the 3V, so to speak, you hardly see any differences between the 3 different speeds. So there's black, red, and blue lines. In the left-hand side, there's hardly any differentiation. So if we only look at the brain activity, the brain doesn't seem to be differentiating between the 3 looming speeds. However, if we look at the right 3, then at the bottom, when the babies are young, there's no differentiation yet between the 3 looming speeds. However, if we move up to the 10, 11-month-old, you gradually see that the black, the red, and the blue lines are differentiating from each other. So that means that we can, if we look at the brain activity itself only, we can see what speed the babies are looking at. So they learn to differentiate that information. So when there's a 2-second loom, it is reflected in the brain activity. So that means, in more traditional terms, that the brain is processing that information. What we see is the brain is reflecting or mirroring that information. That means, if you remember the blue arrows in the traffic situation, we are not producing anything in the brain. We are merely reflecting what is happening in the environment. So there is no strict distinction between the outside environment and what is happening in the brain, or suddenly that the brain is adding something such that speed becomes evident. It's all part and parcel of the same process. So you see, ecological psychology does not have to deny that we have a brain and use it in perception. It is part and parcel of the same process. Only the question is that the brain is used in a different way compared to what we call the traditional movement sciences. Okay, so that is the, now it's 40, okay. So let's move on to one other experiment, which, yeah. So that was the first experiment, and I really showed you three, would show three, but it's not enough time. So let's move over to the third experiment, because this is interesting, because for the first time, we are not only relying on perceptual variables only, because that is more easy to measure with EEG, but for the first time in our lab, we have now incorporated also movement of the arm in the tau coupling procedures. So you see in this experiment we did with students with the same EEG net, where the students are sitting on a chair without too much movement. They put the finger on the red dot on the left hand photograph, and then a little car at the top part is starting to drive. And what the student has to do is try to catch the car when it's going. So the movement of the hand is in Y direction and the movement of the car is in X direction. And what they have to do is to intercept as good as possible. So in this time, we also have the movement of the hand, because in the touch screen, there are many pixels, and we can measure those pixels. So we can have an idea how fast the hand is moving across the screen. And we also know how fast the car is driving. And we also can measure the visual cortex when the subject is looking at the moving car. And we can look at the motor cortex when the finger is moved to intercept the car. So we use the same tau coupling principles in all the things we measure and see how they relate to each other. So for the visual evoked potentials, we look at the back of the head, that is the VEPs. And for the motor area, we look at the top of the head, where the motor cortex is related. And that's, you have to find out what is the best measure for the visual signal and for the motor signal in order to be able to couple that to the rest of it. So this is basically, you can find this in the journal Brain Sciences. And this is what the tau curves look like. Now, they all looked familiar again. They all start from bottom left to top right again. And in the beginning, we have the movement of the car only. So we know how fast the car is moving. But we can also look at how the visual cortex versus the motor cortex are performing in the middle graph. And also the visual cortex versus the car. But we can also look at the car versus the finger. And you see there's all similar principles underlying the task, so that every aspect of the movement is controlled by the same principle. So if we do actually the calculations on that, we have different scales. We can, let's forget about this. We have different scales to have this slope of the regression lines. So you see that, for example, the car versus the finger, you see that the slow speed has a lower K value than the medium speed, 1.11, and also the fast speed is even higher, so to speak. So you can see that there are three different speeds of the car, which you can measure also in the car versus the finger. But you could also look at the same increase when you look at the visual cortex coupled to the motor cortex. You see the same increase in speed. But also when you look at the visual cortex through the car. And so they are kind of related to each other. And by looking at the slope, so to speak, the slope of those lines, we can have a very good insight in how the information of the moving car is reflected in the visual cortex, the motor cortex, the car, the finger, etc. So we can start making those coupling. So the grand average, with quite a number of students taking part in this experiment, of the tau coupling for the K and the K rest for the 3 car speeds. So this is what we called ecological resonance of perceptual motor actions. So we are not enriching the information from the screen and give feedback loops to the movement of the hand. It is rather the information on the screen is reflected in the whole action part of the action capability. So when tau coupling between 2 different scales, the behavioral scales and the electrical scale, the nervous scale, we've showed in this experiment how the concept of tau coupling, so one tau curve against the other, can contribute to the understanding of the concept of what I call ecological resonance, using the coupling constant tau s. So, and between how the variables from the ecological scale, the behavioral scale, relate to the neural scale. And that is where the concept of correspondence, so there needs to be something in the environment, in the temporal structure of the environment, testifying that the temporal structure of the control of the movement is also sustained in the neural control of those actions. So the perceptual information you can measure, and that same information is reflecting in how the movements are being controlled. Now, how is that possible? That is not easy, but people are starting to talk about resonance, and also in the more traditional neurosciences, people start more and more to talk about resonance. Only in the traditional neurosciences, you often see that, here example, in this fly brain, that one part of the brain is resonating with another part of the brain. That they call resonance. But it's not what we call ecological resonance. That is, there needs to be something in the environment where the nervous system is resonating too. So we cannot speak longer of there's perceptual information and there's a nervous system. It's part and parcel of the same communicating process, so to speak. And best to visualize that is maybe this guy who is showing us an example of what we consider ecological resonance. He is going to show that he puts a little sand on a metal plate, and then he puts his finger on the plate, and he's using a violin bow to make the plate into vibrations. And by self-organizing, so to speak, the plate starts making patterns. And we think it's nice to think is a metaphor to think how the nervous system works when we pick up information. Okay, so this is what he
randomization function. Okay, here we go. Nice. A big thank you to the Centre for Life in Newcastle for lending me their Chladni plate. The Centre for Life is an amazing science centre run by amazing people. So go and check it out.
Okay, if we think a little bit about this, that so there's like hundreds or thousands different patterns possible on this metal plate by putting your finger on a different position or putting the bowing action a little different. Now, how do we think about that? This metal plate needs to have some kind of memory structure that every time this guy is putting his finger and his bow at the different plates, it needs to retrieve another pattern in order to comply with the circumstances. We probably also, now that's ridiculous. A metal plate doesn't have a memory for all those patterns. Yet, if we talk about how we control our movements, we do say that, yes, for all the movements we can produce, we need to repeat them hundreds and thousands of times, and they be stored, and we need to retrieve it. We are also this metal plate, which maybe sound a little extreme, but what we have measured so far in ecological resonance is that the information shown to the baby or to the subjects is part of the resonant process. If you look at a guitar, and if you pull the string, you put the string in motion, and then because of the body of the guitar is at the same frequency, when they are both at the same, sound exists. Now, this is also in perceptual motor control. There is the strings, the perception, for example, and the body of the guitar, the neural system, they're part and parcel of the same process. So without the string, it doesn't make sense to look at the nervous system by itself. You always need to look at both in conjunction because it's a system. It's no use of investigating the metal plate in the sand to see how the patterns are formed. And that's what we tend to do in movement science. We look at the nervous system and how it's working without too much attention to that the perception feeding the nervous system or reflecting the nervous system is crucial in order to be able to say something about how the movements are being not controlled. They are reflected, so to speak. So to sum up, that within ecological psychology, it has long been considered adequate to investigate informational variables at the interactive level to describe the relationship between the organism and the environment. So it has long been, like Gibson, he said, no, we don't need to know anything about the nervous system. Knowing how we catch a ball using the tau variable was all we needed in ecological psychology to describe that action appropriately. We now are moving in these international conferences on perception and action. That's the symposium in that conference are making time for also look at how we can look at the nervous system, not in the traditional ways, but how can we use ecological psychology principles to define the nervous system in a slightly different way as is traditionally thought. So most of our results indicated that the sensory integration is not innate, but develops soon after birth when infants start become mobile. So they start crawling around, and by crawling around in the environment, they learn to differentiate that information such that they can distinguish appropriate perception action couplings. And we also presented the concept of equivalent information and the correspondence of tau coupling as a valuable analysis tool to combine the variables. So the fact that tau coupling and I explained you a very simple example of picking up something. That is a very simple procedure. And when you couple perception and you couple the nervous system, you're not longer looking at apples and oranges or apples and pears. You're looking at the tau, how they are changing at the same time. So it's a really nice method to investigate the nervous system, because you can relate it to the environmental circumstances and what's happening into the brain. So I think that's where I leave it today. It's a kind of new step, and it's getting a bit used to. But you have to be able to leave the more traditional ways of having to pick up meaningless information from the environment and then structure it in your brain, and you add your memories, etc., etc. That is the more traditional way of dealing with those things. Here, we've tried to give you more different concepts that are, for me, a more intuitive. For example, if you think about tiny little insects that show incredible perspective control when flying through the air, which don't have big nervous systems. So this kind of way with resonance, to me, is more intuitive in explaining how we move in a cluttered environment and being able to control the actions on the way. Okay, thank you very much. I hope to give you something to think about. And if you have any questions, then yeah.
Okay, so thank you for that. We're going to sit here together so that you both can see us. I think ecological theory is rather new concept. It's less established than in other, maybe the Netherlands, Norway, where you have done Europe, where you have done large parts of your research. And of course, there's going to emerge some questions, and I thought we could take them right now because they're quite good, actually.
Yeah.
So the first one is about aging. So do you think the ecological approach helps explain why many older adults can still move relatively well, even when significant cognitive decline? In other words, could it be because this model relies less on higher order cognitive processing?
Well, as long as the perceptual abilities and the motor abilities of the older persons are intact, so they pick up, they see right, they hear right, then I don't see not why they shouldn't be able to continue doing that. And higher order functions may important when you're walking with that person and talking to it about things, but controlling the movements, we hope, is taken care of by more sort of lower level processes, so that you can, providing the older persons can pick up the information for controlling their actions appropriately. And that is usually also a bit problematic with eyesight and hearing, etc. So, and therefore, that the perception is less, and also the motor as a result of that. Yeah.
Next question is about football or soccer. I'm studying the ecological dynamics and the constraints-led approach, especially in soccer, but I still struggle to understand how skill actually develops. What changes in the player as these processes develop? If learning does not rely on stored representations or motor programs, how does the player learn to perceive and act upon affordances on the field?
Yeah, that's a nice question. It goes more, yeah, you tell me. It goes more, I've now talked about optical flow, but this goes more into the affordances concept. And during learning of football, it's depending on if you are, for example, a small player or a big player, you pick up different affordances for action. If you are a small player, you look at different gaps to pass your opponent, as opposed to if you are a tall player, because you're usually a little bit slower, and you have to have a different strategy to pass your opponent. So it's very much dependent on the body scaling and the action scaling and the level of training, which is how technical you are. And based on how technical you are by training, you learn to perceive different gaps in the opponent. So the more you're trained, the better you're skilled, you know your own capabilities, and you learn to fit your capabilities and training level to your opponent, so to speak. So that is how the affordances process is always dependent on your bodily, if you're tall or small, but also, of course, on your skill level. The better you are, the better you also are to perceive the gaps you need, and not you need to pass a bystander. And that's, I think, what you learn also. It's perceptual motor learning.
Paula had a question, actually. You know, Paula?
Yeah, Paula.
What does ecological resonance reveal about developmental delays or atypical perceptual motor coupling?
I mean, we've done the experiments on babies, with premature babies, for example, and we see that they are different perceptual strategies when compared to normal premature babies, compared to normal born babies. They start their action in the brain earlier than the time-born babies. So they perceive, you can look at the brain and see how well they pick up that information. And the later towards the point of contact, which we found, the better it is, because that you take into account all the information that is there. If you are beginning too early, things can happen on the way. But these premature brains, as we were talking about today, about the parietal, the dorsal stream vulnerability, they lack that quickness in picking up optic flow. So their VEP delay is bigger, and they are picking up the looming information too early. So that's what we can say about, so what that means for resonance. It's because we have a different tau coupling for the premature babies, we say, well, the resonance doesn't function so well. So that it's dependent on the coupling of tau, how well the resonance between the information and the nervous system is going on.
Last question before we go on to Audrey. Does ecological resonance emerge spontaneously, or does it require active exploration?
Active exploration, yeah. You cannot expect that babies are born with this. You need, there's development, and then therefore they need to crawl around in the environment and do things in order for that information to be differentiated. Like in the blue arrows, you need to, from looking at the blue arrows as a beginning driver, you start focusing on, for example, the white lines. If you're driving in Norway in the dark, the only thing you can concentrate on is the white lines you can to go through the curve. Now, you need to learn that as a driver to know which of the blue arrows you have to concentrate on. Not all of them, because some of them are useless. So, and that's also, the baby needs to start differentiating where to pick up the information to catch a ball or hit something or something. Yeah. Mm-hmm. So that would be my answer.
Okay. Interesting.
Okay.
Thank you so much for your interesting talk. We'll transition. So, muito obrigado, Ruud van der Wel, pela excelente palestra. Como combinado, pedimos que quem tiver perguntas, coloque no chat da transmissão do evento 3, o YouTube. que fica à direita do vídeo, tá? Dando continuidade ao seminário, gostaria de apresentar a professora doutora Audrey Vandermeer, PhD em Psicologia do Desenvolvimento Experimental pela Universidade de Edimburgo e professora de Neuropsicologia na Universidade Noruega de Ciência e Tecnologia e possui mestrado em Ciência do Movimento Humano pela Universidade Livre de Amsterdã. Audrey Vandermeer apresentará a palestra intitulada A Caligrafia na Era Digital. Por gentileza, Audrey Vandermeer, fica à vontade para iniciar a palestra.
Yes. So now it's my turn. It's really nice being in Brazil, being back in Brazil. We've been here many times now. And I promised to talk about the importance of handwriting for the brain in the digital area. But we really work in a lab, a baby lab, studying developmental neuroscience in this baby lab. And so about half of my talk is based on how babies learn and develop, our developmental work, but it is relevant for the writing work. So I will finish with the writing and start talking about babies. And 20 years ago, we got this EEG system, high density EEG system, that allowed us to move on from measuring behavior such as reaching, looking, maintaining a balanced posture in babies and children to actually study what is going on in the baby brain as they develop. This system, this EEG system, consists of 128 in the case of babies and 256 electrodes that are sewn together and that in the form of a hairnet, and that we place on the brain, and then we can look inside what is happening inside the brain as babies learn and develop, which is extremely exciting. And this the picture of the baby here is our youngest daughter, Leia. She is 23 now, and she has been helping us with the first experiments on the babies. We have now tested about 500 babies altogether. And I already said Leia is 23 now. She turned 23 in October. And she is a very good futsal player. She plays for the national team of Norway. And last June, she played in Portugal, in Lisbon, against the national Portuguese ladies team. So let's move on to the lab, the Developmental Neuroscience Laboratory, where both Ruud and I are working. And we study development, learning, and also cognitive aging. So we are very interested in developmental processes, learning processes from a lifespan perspective. We study a lot of babies because development goes so quickly in the first few years of life. And we publish our papers in a variety of different journals, and all the journal names with a year in bold behind them, those are actually published master's theses, because we really work from this philosophy that science shouldn't be gathering dust in a corner. All these theses that are being produced shouldn't be gathering dust, but they should be out there. So we encourage our students to write their theses in article form, and all these in bold have actually been published over the past 20 years, 25 years by master students as the first author. I've also been involved in a variety of presenting the research at different platforms, and I often appear in the newspaper. And in 2014, so that's more than 10 years ago, this picture of me holding a baby appeared in a national newspaper, and it had the heading, 1-year-olds are underestimated. And even though it's 11 years ago, I still stand by that statement. And when this was published in the newspaper, it went viral. The article went viral because 40,000 people clicked to read the article in the newspaper in the course of only 2 days. And the thing is that we in the West, at least, we have this tendency to underestimate our babies because they move in a clumsy kind of way, and they don't have any language. And that makes us believe or assume that the baby brain is immature, and that these babies, that their brains have to mature during the first few months of life before they can start really voluntary and purposefully interact with the world. So the purpose of our lab is to show experimentally that, in fact, our babies are much more clever and much more smart than we give them credit for, and that they actually are born with a brain that is ready to learn from day one. So we have been carrying out a number of different experiments, all showing that our babies are much smarter than we think they are. For instance, we have a paper on sucking behavior, which the sucking reflex is a well-known neonatal reflex. All babies are born with it, and is often used to explain why babies are capable of drinking milk from the breast or a bottle from day one. But when you start thinking about it, when feeding, you don't only need to suck, but it's actually a very coordinated, it's about a very precise coordination between sucking, breathing, and swallowing. And that is what we find, that babies, when feeding properly, at only 2 to 3 days after birth, they suck, breathe, and swallow in a 1-to-1 coordination. And if there is a problem, then babies are capable of sucking and swallowing, but they can't breathe at the same time. So you get these short bursts of sucking and swallowing, but the baby is not breathing at the same time. It's not capable of coordinating breathing with the sucking and the swallowing, and therefore they have only short periods of sucking and swallowing behavior. They turn a little bit blue in the face because it's anaerobic, and then they have to take a break fairly quickly after maybe 10 seconds. They need to catch their breath, and then they start sucking and swallowing again. And it says itself that this is not a very economical way of drinking milk, and it may make the baby to get very tired before it's completely satisfied, and then you quickly end up in this negative spiral of falling asleep before it's completely satisfied, waking early, and you have that problem with sleeping, feeding, and so on. Another project is, a recent project is about the fact that we have been trying to find empirical evidence that newborn babies born of Norwegian-speaking parents, that they cry in their mother tongue when it comes to the melody and the intonation of the crying sounds. And that would mean that if newborn babies cry in their mother tongue with the characteristics of Norwegian or Italian or Portuguese, that these newborns, they must have picked up the characteristics of their native language already when in the womb. And it also has implications for babies who are born with a hearing deficit, because they haven't been able to pick up those characteristics of their native language, and they would then consequently cry not in their mother tongue, not showing the characteristics of their mother tongue. So you can see at this on this slide there, we have many different projects. The latest one is the Skate Babe project, which is a skateboard invented by a French Olympic skateboarder. And we put very young babies, before they start crawling themselves, we put them on the skate and we see if they can start using their crawling reflex to start exploring the world around them. So underlying all this baby research is that it is often said that we have a brain to think and feel, do these mystical things with. But in our perspective, we rather say that we are not our brains, but we are our bodies, and that movement is the brain's language. So we come from an embodied and an active cognition perspective, where movement is considered to be very important, and also the body. So what is a brain for? And it's a moving story, they say. And we know, for instance, that baby rats who are allowed to grow up in a gymnasium where they have climbing possibilities and hamster wheels and tunnels and so on, that their brains are much more advanced. They show much more dendritic branching than normal rats, young rats that are raised in a normal, what's the word? A normal cage. And also our children, so they need to have to receive the opportunity to move from an early age. The sooner, the better. So the past 24 years or so, we have been mapping the infant brain, both with high-density EEG, and now also since 2 years with FNIRS, functional near-infrared spectroscopy, and not only to find out how normal brains develop during the first year of life, but also to see how, for instance, the preterm brain develops and what kind of challenges the preterm brain has, and so that we can maybe make an earlier diagnosis and start helping those babies that are born too early. And exactly a week ago, it was World Prematurity Day, where important buildings all over the world, they are lit up in the color purple. So, for instance, Sydney Opera House is lit up in that color. We have a rock museum in Trondheim, which is called Rockheim. And that is also on November 17th, lit up in the color purple. I don't know if you do that in Brazil, but it is important because many people in the world are now born prematurely. 1 out of 10 is born prematurely. And the incidence of preterm birth in Brazil is even 12% rather than 10%. So, and not all of these preterm babies develop problems, but many of them do. And then it's important to diagnose them early so that some intervention can take place. And research from our lab from the past 25 years shows that the onset of crawling, of self-produced locomotion, gives a boost to the infant brain. And that is maybe not so surprising, because if you're only capable of lying flat on your back, staring up at the ceiling, you don't need advanced neural networks to judge velocity, distance, time to collision, direction, and all these kind of important things. But as soon as a baby becomes mobile itself through crawling or walking even, then you need to be able to assess these, make these timing and directional decisions quickly and accurately. It's easier to promote learning and to prevent learning problems, with very small babies and young children, because there's so much happening in the young brain. The volume and the weight of the brain doubles in size during the course of the first year. And the nerve cells in the brain, they increase in number, they become more specialized, and they make more connections with each other. And then we're talking about up to 1,000 new connections per second during the first 2 to 3 years of life. So an awful lot is happening. And it can be said that the first 1,000 days of life form the basis for the brain's infrastructure. So the developing brain is very open and plastic. It can adjust to circumstances that surround it. And the brains of young children between 0 and 3 years of age shows enormous plasticity. So you can compare it to the newborn brain consisting of faint paths in the forest, and through varied input and lots of experiences, those faint windy paths, they transform into motorways that quickly and efficiently transport information and knowledge. And also the brain works according to this principle, use it or lose it. So if you have formed or helped your baby to form these important neural networks, then it, just like a modern road net, you also have to maintain those networks. So it's not enough to help your baby to form those important neural networks to deal with the environment in best possible way, but the baby also needs to maintain these networks. So from our perspective, it is very important for the self-produced movements are very important. And this is confirmed by research of more than 60 years old, where they held in Hein, physiologists, they studied pairs of kittens, and the kittens were exposed to vertical lines. And the only difference between a pair of kittens was that one was allowed to go itself, being exposed to these vertical lines, whereas the other was driven around in a kind of gondola. So the visual exposure was exactly the same for both kittens. The only difference was that one was allowed to go itself, whereas the other was driven around. And then Heldenheim found that only the kitten that was allowed to go itself developed normal vision. The other kitten had difficulty with depth perception and all sorts of other problems, visual problems as well. So it's important also for the baby's cognitive development to come out of this supine position and start moving around, so that the baby can really begin to understand difficult concepts like in front of and behind, or below and above, for itself, by crawling around in its environment and perceive for itself what the world looks like from under the table or from up in the curtains. It's almost impossible to really understand these cognitive concepts without self-produced movements. So that means that we have to help our babies out of this supine position that doesn't do anything for their brains. And we can do that by taking the babies to baby swimming, by carrying our babies in a sling in an upright position, so that the baby can develop muscles in the neck that are strong enough to carry its own head, so that head-eye coordination can start to develop, and also so that it can develop muscles in the arms and legs that can lift the arms and legs against gravity. But probably the most important intervention with very young babies is to give them plenty of tummy time, putting them in a prone position, which is a normal crawling, a natural crawling position, and also it helps them to build neck muscles strong enough to carry that big brain, the big human brain. And actually, the World Health Organization recommends 30 minutes of tummy time a day from birth until the baby starts crawling itself. And recently, we have published a paper that almost for the very first time shows that babies that are receiving extra motor stimulation in the form of baby swimming or baby massage, that they show advanced brain development compared to full-term control infants and infants born preterm. Tummy time is also can be considered a kind of a scaffolding skill for other developmental areas. So 4.5 years ago, I became a grandmother to identical twins, and I instructed my eldest daughter that she should take the babies to baby swimming, that she should carry them around in a sling, in an upright position, and that she should give them plenty of tummy time. And she, believe it or not, she listened to me and she did all those things. So, but when Cleo and Nikki, the twins, were 3 months of age, they were very comfortable on their tummy. And they used this newly developed motor skill to start developing in other developmental areas like language and communication. So I'm going to show you a short clip where the twins basically for the first time acknowledge each other, and they helped by their advanced skills in a prone position, they start using that skill as a scaffolding skill to communicate with each other. Okay, so enough about cute babies now. Now I'm going to show you why we remember things better when we write them down by hand. But remember that the concepts I talked about in terms of the baby's development also apply to these handwriting studies. So in 2015, we were approached by Microsoft, who had learned that we have these electrode nets, and we actually have them from newborn to adult size. We have many different sizes. And Microsoft said, okay, can you find differences in electrical activity in the brain when we're writing as opposed to when we're typewriting? And initially we were quite skeptical because we didn't think that our system would be sensitive enough to actually pick up these minute differences. But it turned out that they weren't minute differences, that the brain works completely different when you are using your hand to write or draw, as opposed to when you use a keyboard to type. And so we started looking around in the existing literature. Remember, this was in 2015. And then we found a newly published paper by Müller and Oppenheimer, two Americans, who had not done any brain research, but they had college students watch TED Talks, and half of the groups were taking their notes by hand, whereas the other half of the group used a keyboard and a computer to take their notes. And then they received a test afterwards, and Müller and Oppenheimer found that the two groups scored the same when it came to factual knowledge and questions, but when it came to conceptual knowledge, the group who had taken their notes by hand outperformed the group who took their notes on a keyboard. So we took this study. Remember, it's not brain research, but we took this study as a starting point to carry out our brain research. So we, since 2015, when we started, we have published 3 different papers on the topic. The last one in the beginning of 2024. And we have since then been contacted, and we have many collaborators. Microsoft is one. We are involved with Moleskin, Pagani pens, pen manufacturers. The big pens are one of our collaboration partners. And recently, in February of this year, I joined the scientific advisory board of Remarkable, which is a Norwegian paper tablet company that has all its special philosophy. And so they produce these tablets, and they come with a digital pen. They are not connected to the internet, so you can't receive your emails, but you can download PDFs, and then you can highlight them, use color, and so on and so forth. But they want their tool to help you be creative and to think better. So again, we used our adult nets to test students mainly, but also 12-year-old children. And we played the game Pictionary with them. So they were presented with a word on a screen, and then they either had to type that word, they had to give a description of the word through typing, or they had to draw the word or write the word by hand, divided over the 3 different experiments. And we basically found that handwritten notes are best for memory and learning, and that our research shows that children remember better and learn more when they're writing by hand. And I'll go and lead you through the 3 different experiments. So the first experiment from 2017 was done on students, where they had to draw or type different words. So it could be ice cream, that they had to write on the keyboard ice cream, ice cream, ice cream several times, or they had to give a description of the word ice cream without using ice cream, or they had to draw an ice cream. And some of the words were very concrete, whereas other words would be more difficult, like friendship or birthday party or something like that. And then in the second study, this is our master student Eva, and actually Sergio, he was in Norway when she graduated, and he was her external examiner, and he gave her a very good grade. And this paper has been become most popular so far, where we added a group of 12-year-old children, and we also for the first time included a handwriting condition, because the previous experiment, we didn't use handwriting, we only used drawing, under the assumption that the neural mechanisms underlying drawing and handwriting are the same. But since we didn't test it, this was only an assumption. But in this second paper, we actually showed that indeed handwriting and drawing have the same neural mechanisms, underlying neural mechanisms. So here we have a 12-year-old boy who has drawn a piece of cake, and he writes cake, cake, cake several times. And we have a 23-year-old female student who has drawn an umbrella and also has written umbrella in several times. And then we see that comparing handwriting and drawing to typewriting, we see that during handwriting and drawing, the brain is much more active than during typewriting. And also, when more parts of the brain are active, then the brain is in need of communicating between its active parts. And it does this through neuronal oscillations. And these oscillations, they can take place either in synchrony in red or in desynchrony in blue at different frequencies. And we see that during handwriting and also during drawing, the brain is oscillating at low frequencies in a synchronous manner, and it's oscillating in desynchrony at higher frequencies. And it's easier maybe to see here when we subtract typewriting from handwriting, we're left with the surplus activity during handwriting or drawing. And we see that, especially in the back of the brain, we find these low-frequency synchronized activities in most parts of the brain, and we find desynchronized activity at higher frequencies as well. And other literature has shown that low-frequency synchronized oscillations in exactly those parts where we find this kind of activity are beneficial for learning and remembering. And then the last study in the beginning of 2024, we looked into brain connectivity to look at the functional connections in the brain, again during handwriting and during typewriting. And then you go through a pipeline where you end up with network measures, where you have hubs that are showing very many connections between brain regions, and nodes and the connecting edges between them. And then if we look at handwriting, we see widespread brain connectivity throughout the whole brain. It's like the model here in B is wearing a party hat. And if you look at the same picture for typewriting, there's no such activity, no such connections at all. The activity is completely, or the connections are non-existent, basically. So already in 2018, the National Science Foundation made this educational brief video that I'm going to show to you now, which sums up our results very clearly.
Today, many students have traded pen and paper for a keyboard and screen.
Wow.
But when it comes to taking notes, is typing as effective as old-fashioned writing? It might be more time-consuming, but a new study shows writing by hand may offer benefits over typing on a computer. Scientists used EEG technology to examine the brain activity of 20 undergraduate students as they took notes during a word activity. They found regions of the brain associated with learning were more active when the participants drew descriptions of the words they saw by hand, as opposed to taking notes by typing the descriptions. Authors of the study say their findings suggest writing or drawing by hand promotes deeper encoding of new information in ways that keyboard typing doesn't. It may also improve a person's memory for new information, as handwriting involves rich sensory motor experiences that help stimulate the brain. So don't overlook the old-fashioned pen or pencil when it comes to helping your child learn. I'm Jessica Sanchez reporting.
Yeah. Also, in January 2024, 20 states of the United States decided to reintroduce handwriting tuition as part of the curriculum based on our research. And also in Canada and Sweden, and in the rest of Europe, there are loads of discussions going on that we need to instruct our children to write, basically, because it's such good brain stimulation, but also because we want the next generation to be able to write a love letter or a poem, or at least a grocery list by hand, because it's so good for their brains. And these three studies combined, they have received an awful lot of media attention, even now, almost 2 years after the last publication in the beginning of 24. I'm contacted at least twice a week by journalists who want to speak to me. The handwriting research has been in Scientific American last year, in National Geographic also. All this is last year, and it has even been on Puberty, which is a social media platform mainly used by young people. And I remember very well that one Saturday evening we were watching television, and then suddenly our kids started posting things like, that feeling when mom and dad's research is being discussed on puberty. So I took contact with one of my kids and said, is this good or bad? And they were saying, no, it's very good. And it reached almost 500,000 likes within a very short period of time. So it's very, everybody seems to have a meaning about handwriting, especially teachers, journalists, and those kind of people. And many people say, thank you so much for doing this research and showing the importance of handwriting in the digital age. And then in 2015, when all this research, brain research started, in Norway, there were completely digital schools popping up like mushrooms. And there, the 6-year-old children who started school, they were given a tablet, and they should learn to read, write, and count on the tablet. They should work on the tablet all day during school hours, then take the tablet home to do their homework on the tablet, then maybe watch some television, and maybe play some games on the tablet themselves. So an awful lot of screen time for these very young children. And we now have urged the Norwegian government to make some national guidelines to ensure that pupils receive a minimum of handwriting tuition. The argument has always been that it's good for young children to give, if they learn to read and write through a tablet, then they can start expressing themselves in written form earlier, and that helps especially young boys with the motivation to learn to read and write. But we now know that children who have learned to read and write on a tablet, they often have difficulty both when writing and reading with letters that are each other's mirror images, like the B and the D. Because we think it's because they haven't felt with their bodies that a B is produced in a completely different manner than the D is, for instance. So it's so important to produce those letters by hand, to learn to spend many hours writing these, forming these words on paper, because it's so good for their brains. But nowadays, because of the mobile phones and so on, primary school teachers of grade 1, they complain that they receive 6-year-old children in their classes who barely know how to hold a pencil. So that means that during kindergarten, they haven't been doing the coloring, they haven't been doing the puzzling and the practicing the fine motor skills that help them in their later writing tuition. So in 2020, during Corona, a book came out by a young father, a father of 3. He's also an architect and a writer, an author. And he called his book The Digital Guinea Pigs. And he wonders whether today's children really need more digital competence, or do they have this competence already, and are they in need of other and more complementary skills, such as the ability to specialize and concentrate over longer periods of time? And he feels that, in his case, the Norwegian government has introduced these digital tools too early and without doing a consequence analysis, and that we now may have problems with the next generation who isn't able to write. And there are already articles in the American press that say that the current generation can't even produce a signature anymore. Also in Norway, they introduced digital praxis in kindergarten. And then it's important to remember that the kindergarten's digital praxis is supposed to support children's play, creativity, and learning. So in the kindergarten, they also have this requirement that children should receive teaching about digital teaching and in order to become digitally competent. But recent research from Sweden and England has shown that play in kindergarten becomes less creative when children use a tablet. And research from 2023, where more than 7,000 Japanese mother and baby diets were tested, they showed that heavy use of screens in 1-year-old children was related to reduced communication and fine motor skills, both at 2 years and 4 years, and delays in problem solving and personal social skills were found at age 1 and 2, but no longer at age 4. So important negative consequences of heavy screen use that new parents should be aware that that is actually a problem, and that young children should be using their bodies and all of their senses to explore the real world rather than actively consume a virtual world behind the screen. And that's what I have been saying for at least 10 years now. It's not really what young children do behind the screen. It's all they miss out on. Young children under the age of at least 3, but probably 4, they can't afford to waste their valuable time by experiencing second-hand experiences behind the screen. They should be actively be out there using their bodies and all of their senses to touch and both in inside and outside, in good weather, bad weather, to climb in trees and do all these kind of things, rather than sitting still on their bottom and engaging in a passive way with the screen. Screens don't smell, they don't taste, and babies especially need real people to interact with, not through a screen, and that talk to them. It's also very important for language development. And here I'd like to mention the recommendations of the World Health Organization again for babies under 1 year of age. We see this tummy time is very important, where babies are placed on their tummy at least 30 minutes a day, spread out over the day, obviously, and they shouldn't be restricted for more than 1 hour at a time, not even attached to their mother's body or in a pram. And screen time is not recommended at all for babies under 1. And when they are sitting in a high chair or in a pram, they should be, the parents should be engaging in reading and storytelling with a caregiver. So a lot of time on the floor is where the baby is able to move freely, roll around, lie on its tummy, and so on. That is very important for a young child's development of early motor skills, so that they can also start developing their language skills and their communication skills. Then finally, if you are able to give your child a bilingual upbringing, that is very recommendable, because learning a second language is also, next to handwriting, is also very good brain stimulation. You could even try baby sign language, where, you know, if you start early enough, around 8 months, then babies have much more understanding of language than that they can produce, because producing the sounds belonging to the different words and expressing themselves, that is actually quite difficult. But you can teach a baby sign language, and then an 8-month-old baby is able to say that it's using sign language, that it's thirsty and wants milk, not water. And it's really crazy to see that such young babies can actually use this to communicate. Also, there's no app to replace your lap. Read to your child, talk to your child, engage in storytelling activities on the floor, talk all the time to your baby, even though you think they won't understand. They do understand much more than we give them credit for. So when you're changing your baby's diaper, you can talk about that it's so cold outside, and that today you're putting on the child's green socks, and so on. You just talk and talk and talk, and they will absorb it like little sponges. And recent research from Norway has shown that 1 out of 3 parents report that they read no or very few books to their children, which is a real shame. I mean, 2 out of 3 parents do read regularly, but 1 out of 3 parents do not read to their child. And reading is such a nice activity, and it's very important for a child's language development. And it turns out that the child's own interest for reading is related to how much it is being read to. Then, very, very briefly, last year we were involved in this Norwegian documentary series where 2 young fathers voluntarily logged themselves off their smartphones and their computers for a whole year. And they, after this experiment, they said that the brain should sue the smartphone because they really saw the benefits of. And actually, the one on the left, he's a professional football player, and he played together with Mats in the football. And he's also a writer of children's books now, and he's a PE teacher. And he writes these children's books about football so that especially young boys will want to pick up a book. And what we did in this experiment consisting of only 2 participants was that we measured their brain activity while doing the Pictionary task that I showed before they logged themselves off, then 6 months after they were logged off, and a year after they logged off. And the brain results, we looked in terms of connectivity, and we found that there was a massive increase in number of functional network connections after only 6 months without a smartphone. And again, this is only 2 subjects, but still you can clearly see that. So T1 is when they were still online as a Norwegian teenager, which means at least 6 hours a day. And T2, you see this increase in connectivity in these connections, maybe more so for the described condition for Mike, and mostly maybe for the right condition for Sven. So that is all. I would just like to finish by saying a big thank you to all these babies and their parents who've been helping us with this research about brain development. Thank you very much.
All right. Yeah, thank you so much, Audrey van der Meer. Really exciting and interesting to see how we might have been misled with all this new technology during these years. And I probably speak on the behalf of many here that I don't write anymore. And if I write something, if I need to take notes, it's all on the phone, it's all digitalized. So we have some questions surrounding this. Regarding our children, because they're the ones learning the most and the most rapid, as we've seen. How can teachers integrate digital devices without compromising perceptomotor development linked to handwriting? This is a question from Paula again.
Yeah. I mean, sometimes we are criticized for wanting to go back to the Stone Age where we were writing in stone. This is not what we're saying. We're just saying that for every task in the classroom, you have both the pupils, the students, and the teachers and the professors. They have to decide which is the best way. And what our research has shown is that when you take notes in a classroom because you want to learn from your notes for the exam, it is much better for the brain. You learn more and you remember better if you take the notes by hand. But obviously, if you're writing a book or a long essay, then it's much easier to use the computer and the keyboard, and you have your spell checker and everything at hand. Then it obviously is allowed. So for every task, but note-taking, when it comes to note-taking, it's very important to take the notes by hand. And that also explains why if you can't make it to a lecture and you borrow the notes from your mate who did go to the lecture, they don't make sense because the the fact is that if you take notes by hand, you can't write down everything that is being said. You have to process the incoming information, and you can only write down keywords, boxes, arrows, and underlinings. Whereas if you're taking notes on a keyboard, you can actually type so fast that you type down everything that is being said. But it gives a false security because it's coming in through your ears and it's coming down, going out through your fingertips, and you're not really making the material your own. You're not processing the incoming information, and that's why it doesn't stick.
Yeah, this ties into the next question I saw. You mentioned the richer sensory-motor activation during handwriting. Do we know whether it's the motor complexity itself that matters, or is it the lower pace forcing deeper processing?
I think it's both. I think it's the fine motor skills involved in handwriting that is very important. The use of your body and all of your senses, but also because it's going slower, you are processing the information and linking it to knowledge you already have and making it personal to your skill level, your personal skill level.
So how is a D on a keyboard different than actually writing it? Why do I learn less by just pressing a button?
Because whatever you try to type on a keyboard, it only involves very simple finger movements that are exactly the same for every letter that you want to type. Whereas if you write an A, it's completely different underlying motor pattern than writing a B. And that's why young children in Waldorf schools, they form the letters with their bodies and they write their own recommended literature. They write everything and they use a lot of drawing in the classroom as well.
Interesting. Do we have time for one last question? Yeah. One last question from Sabrina. How can atypical children who depend on technology and rely on typing instead of handwriting be included in learning in a way that is less harmful to their perceptual motor development?
Yes. Of course, when it is a learning aid, then the keyboard is the best thing to have. When you have a child with CP who can't write using a pen but can write using a keyboard, or even make letters by eye movements, then of course that's the next best thing. So I'm only talking about healthy normal development, children that follow a normal path. But if you need, in order to perform in a normal classroom, if you need learning aids, then they are involved. They are allowed. Yeah.
Okay. Thank you so much. I would like to invite Paula, Doutora Paula, to say some last final words before we end this event, just to, as a last little goodbye. And again, thank you. Ruud is behind there. You don't see him, but thank you to him. And thank you to Audrey van der Meer as well. They're actually married, if you didn't know. So they're traveling the world together, doing some talks. And it's very nice to have them here in Bauru, Brazil. Thank you to everyone who watched. And Paula, the word is yours.
Thank you. Boa noite a todos e a todas. Então, nós chegamos ao encerramento desse quarto seminário de comportamento motor. E eu, juntamente com o professor Sérgio, gostaríamos de expressar nossa profunda satisfação por esse encontro. Embora nós tenhamos, né, uma programação bem enxuta, né, com apenas 2 palestras, vocês puderam ver a qualidade das discussões, a profundidade que foram faladas, né, das reflexões que foram feitas aqui, mostrando a força e a relevância da área de comportamento motor. Eu quero agradecer de forma especial aos nossos palestrantes convidados, ao Dr. Ruud, a doutora Audrey, que gentilmente aceitaram o convite e compartilharam conosco seu conhecimento, suas experiências e suas perspectivas. I'm a very special thank you to Dr. Ruud and Dr. Audrey. We are truly grateful for your time, your insights, and your generosity in sharing your experience with us. Your contributions made this seminar exceptional. Thank you so much.
Thank you.
Da palestra do Dr. Rude, eu gostaria de destacar essa relação que ele fez, muito importante, com o sistema nervoso e a perspectiva ecológica, e as noções de fluxo óptico, tal, com as atividades cotidianas e esportivas. Da palestra da doutora Audrey, eu gostaria de destacar os estudos em neurociência desenvolvimental e as mudanças no cérebro do bebê ao longo da vida, além da importância da escrita à mão para o desenvolvimento percepto-motor, memória e aprendizado. Suas contribuições foram fundamentais para enriquecer esse seminário e certamente seguirão inspirando nossos estudos e práticas. Gostaria ainda de agradecer à comissão organizadora, os membros do LIVIA, do Laboratório de Informação, Visão e Ação, pelo empenho em cada detalhe e esta organização. Muito obrigada. E também ao público que está aqui presente, pela participação atenta, pelas perguntas interessantes e pelo interesse demonstrado ao longo do evento. Que as ideias que surgiram aqui hoje continuem em nossas pesquisas, colaborações e iniciativas. É assim que fortalecemos a área de comportamento motor e ampliamos o seu impacto. Muito obrigado a todos e a todas pela presença. Tenham uma excelente noite e até o nosso próximo encontro. Obrigada.